Hi, welcome to Learning Outcome 2.2. This is convolution of two continuous time signals. We've done convolution of two continuous time signals before, which was also Learning Outcome 2.2, but now we're going to look at functions with non-constant values. They work pretty similar, but there's a few small details you need to work out. Here's an example. We're going to have a different h of t, and you see it's a ramp, time-limited ramp. Same convolution integral we had before, tau equals negative infinity to positive infinity, x of tau, h of t minus tau. Our h of t is a time-limited ramp. It's equal to t from 0 to 1, 0 else. Our x of t as a constant value between 1 and 3. Our h of t is a time-limited ramp. We can convert both of them into an h of tau, x of tau, just by replacing the variables. It doesn't change any. What's a little bit different now is that our h of tau also has a tau value in the equation, and that has to be changed as well. I want you to figure out what the value of h of t minus tau would be for the h of t which we're using for this problem. If we see a t, substitute in a t minus tau, and then simplify some things. Pause the video and do this calculation. When we work things out, we've got an h of minus tau, which does a flipping of our signal, same as we've seen before. Mathematically, we're really looking for h of t minus tau, where h of t minus tau has our flipped signal, similar to what we had before. The range of values is t minus 1 to t, as we've seen before. But now let's take our h of t, and we'll replace all of our t's with a t minus tau. When we do this, we have our h of t minus tau is t minus tau from 0 less than t minus tau less than 1. We then work on some algebra. We can multiply through by -1. That makes our tau positive. We can add t to all terms. Then we can rearrange things such that we have the greater than symbol we're used to using. Notice that our t value became a t minus tau, and that's the value of our function in the region between t minus 1 and t. We now work through our cases the same way we worked through them when we had constant values. We start off with t at negative infinity, and we gradually move it to the right. When t is starting at negative infinity, we have no overlap because we have functions that are limited in time, non-zero in a limited range of time. Case 1 is when t is less than 1, and our y of t is 0 because there's no overlap. Case 2, we have some overlap. This is going to be valid when our t minus 1 is to the left of 1. And it's also going to be valid when our t is greater than 1, or t is to the right of 1. We merge the two of them, we have the range of time between 1 and 2. Now to look at our convolution integral value for y, this is going to take on values where we have non-zero values. When tau is less than t minus 1, both functions have a value of 0. When tau is between t minus 1 and 1, our x of tau is a value of 0. And when tau is greater than t, our h of t minus tau is 0 for all those values, and sometimes x of tau is also. But only when our tau values between 1 and t are both of them non-zero. In this case, our x of tau is a value of 1, and our h of t minus tau has that t minus tau you calculated a little bit earlier. That's our integral that we want to work on. You should now take some time and figure out what is that integral, what does it evaluate to? You know how to do this. It's a little bit trickier now because we've got our variable of integration, which is tau, and we've got t's and taus involved inside of here. So watch that really carefully and pause the video and do this calculation. I hope that when you do this calculation, you came up with y of t is t squared over 2 minus t plus 1/2. If you didn't get that, go back and check your math. You probably dropped a negative sign or a parenthesis was missing. But I'm sure you can do this. This is stuff you had in Calculus 1. It hasn't changed any. You're just a little bit rusty, but you can do it. When we look at our final answer to this point, we've done two cases. We want to write everything out as we're doing our work. Case 1, our y of t is 0. This is valid when t is less than 1. And case 2 is this integral, which you can also evaluate and put in the evaluated value. This is valid for 1 less than t less than 2. We now move on to case 3. This is valid. This is where we've got total overlap. Our h of t minus tau is totally enveloped within the domain of our x of tau. This is the case when t minus 1 is to the right of 1, or t minus 1 is greater than 1, which is equivalent to t is greater than 2. It's also valid when t is less than 3, or t is left of 3. In total, this is when t is between 2 and 3. Our convolution integral, range of limits of integration, is where both of them overlap with non-zero values, and that's in that middle region between t minus 1 and t. Those become the limits of integration. Our functional values, our x of tau is 1, h of t minus tau is t minus tau, so our y of t is the integral from tau equals t minus 1 to tau equals t of 1 times t minus tau. Again, you should be able to integrate and evaluate this integral. And our answer to this point shows all three cases with our y of t's and our range of values in which they're valid. Case 4, we're moving our h of t minus tau further to the right. Now there's a little bit of partial overlap. It's when our t minus 1 is still smaller than 3, to the left of 3, or t is less than 4. And when our t is to the right of 3, or t is greater than 3. This is our range from 3 less than t less than 4. Again, working on a convolution integral, where we have the non-zero overlap is between t minus 1 and 3. That gives us our limits of integration, and our functional values are the same. So our answer to this point now shows all four cases, all four y of t's, and the range of function of time in which each of those cases is valid. Our final case for this example is when now t is great enough that we now have our h of t minus tau totally to the right of x of tau. This is when t minus 1 is to the right of 3, or t minus 1 is greater than 3, and t is greater than 4. Because there's no overlap, our y of t is 0. Our final answer, we're now showing all 5 cases, each one with our y of t and our range of t's where they're valid. When we integrate each one of those, we wind up with our y of t as this piecewise defined function, and I went and plotted it with MATLAB. You don't need to plot these usually. Occasionally I'll ask you to do this on homework, but it is really good to check all of those endpoints and see that we've got continuity. If we don't have continuity, you probably did something wrong. If you do have continuity, there's no guarantee you did it right, but your chances are much greater at that point. Go back and work through this. Make sure you can integrate each of those cases. Make sure you see why we got each of the times when each one is valid, and why we got each convolution integral, particularly the limits of integration and the arguments within.